An AC bridge is a circuit that uses an alternating current, AC, source and a detector to measure the unknown impedance of an electrical component, such as a resistor, an inductor, or a capacitor. An AC bridge consists of 4 arms, each with some impedance, that are connected in a square or rhombus shape. The AC source and the detector are placed in opposite diagonals of the bridge. The bridge is balanced when the ratio of the impedances in one diagonal is equal to the ratio of the impedances in the other diagonal. This condition allows us to calculate the unknown impedance using the known impedances. Some examples of AC bridges are Maxwell's bridge. This bridge is used to measure medium inductance. It has one arm with a series combination of a resistor and an inductor, another arm with a parallel combination of a resistor and a capacitor, and 2 arms with resistors only. Hayes bridge. This bridge is used to measure high inductance. It has one arm with a series combination of a resistor and an inductor, another arm with a parallel combination of a resistor and a capacitor, and 2 arms with resistors only. The difference from Maxwell's bridge is that the capacitor is placed in the same arm as the unknown inductor. Steering bridge. This bridge is used to measure capacitance and dissipation factor. It has one arm with an unknown capacitor, another arm with a standard capacitor, and 2 arms with resistors only. Wien bridge. This bridge is used to measure frequency and phase angle. It has one arm with a series combination of a resistor and a capacitor, another arm with a parallel combination of a resistor and a capacitor, and 2 arms with resistors only. AC bridges are very convenient and give accurate results of the measurement. They are also used for other applications such as communication systems, complex electronic circuits, etc. A Maxwell inductance bridge is a type of AC bridge that is used to measure an unknown inductance of a circuit or a device by comparing it with a known inductance or capacitance. It is a modification of the Wheatstone bridge, which is used to measure an unknown resistance. A Maxwell inductance bridge can have 2 forms: Maxwell's inductor bridge and Maxwell's inductor capacitance bridge. In Maxwell's inductor bridge, the unknown inductance is balanced by a known inductor and a variable resistor. The balance equation of this bridge is independent of frequency and is given by where $L_1 is the unknown inductance, $L_2 is the known inductance, $R_3 and $R_4 are variable resistors. In Maxwell's inductor capacitance bridge, the unknown inductance is balanced by a known capacitor and a variable resistor. The balance equation of this bridge is also independent of frequency and is given by where $L_1 is the unknown inductance, $C_4 is the known capacitance, $R_2, $R_3 and $R_4 are variable resistors. The advantage of using a Maxwell inductance bridge is that it can measure low Q or medium Q inductors with high accuracy. The disadvantage is that it requires a variable inductor or capacitor, which can be expensive and bulky. A Maxwell inductance capacitance bridge is a type of AC bridge that is used to measure the self-inductance of a circuit by comparing it with a known capacitance. It is based on the principle that the phase angle of an inductive impedance can be cancelled by the phase angle of a capacitive impedance when they are in opposite arms of the bridge. The bridge is balanced when there is no current flowing through the null detector, which means that the voltage drops across the opposite arms are equal in magnitude and phase. The unknown inductance can then be calculated from the values of the known resistances and capacitance in the bridge circuit. The diagram of a Maxwell inductance capacitance bridge is shown below. Plus dash 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 plus dash 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 dash. R1 and L1 are the resistance and inductance of the unknown coil, R2, R3 and R4 are known resistances, C4 is a known variable capacitor, and D is a null detector. The balance equations for this bridge are and. You can find more information about this bridge and its applications from these sources. I hope this helps you understand the concept of Maxwell inductance capacitance bridge. Hayes bridge is a type of AC bridge circuit that is used to measure the self-inductance of a coil with a high quality factor, Q10. It is a modified version of Maxwell's bridge, which is suitable for measuring coils with a medium quality factor, 1, Q10. The bridge consists of 4 arms, AB, BC, CD, and DA. The arm AB contains an unknown inductor L1 in series with a resistor R1. The arm CD contains a standard capacitor C4 in series with a resistor R4. The arm CD contains a standard capacitor C4 in series with a resistor R4. The arm CD contains a standard capacitor C4 in series with a resistor R4. The arm CD contains a standard capacitor C4 in series with a resistor R4. The arm CD contains a standard capacitor C4 in series with a resistor R4. The arm CD contains a standard capacitor C4 in series with a resistor R4. The arm CD contains a standard capacitor C4 in series with a resistor R4. The arm CD contains a standard capacitor C4 in series with a resistor R4. The arms BC and DA contain pure resistors R3 and R2 respectively. A detector or galvanometer is connected between points B and D to indicate the balance condition. An AC source is connected between points A and C to supply the bridge. The balance condition of Hayes bridge is achieved when the voltage drops across AB and CD are equal and opposite, and the voltage drops across BC and DA are equal and opposite. This means that no current flows through the detector, and its deflection is zero. Using Kirchhoff's voltage law, we can write the balance condition as Z1 Z4 is equal to Z2 Z3, where Z1 Z2 Z3 and Z4 are the impedances of the four arms. Substituting the values of impedances, we get R1, JX1, R4 plus JX4 is equal to R2 R3, where X1 is equal to 1 omega C1 and X4 is equal to omega L4 are the reactances of the inductor and capacitor, respectively. Expanding and equating the real and imaginary parts, we get R1 R4, X1 X4 is equal to R2 R3. R1 X4 plus R4 X1 is equal to 0. Solving for L1 and R1 we get L1 is equal to R2 R3 C4, 1 plus omega 2 R4 to C4 2. R1 is equal to omega 2 R2 R3 R4 C4 2, 1 plus omega 2 R4 to C4 2. The quality factor of the coil is given by Q is equal to omega L1 R1 is equal to 1 omega R4 C4. These equations show that L1 and R1 depend on the frequency of the source omega. Therefore, to measure them accurately, we need to know the exact value of omega. However, for high Q factor coils, we can neglect the term 1 omega 2 R4 to C4 2 in the denominators and simplify the equations as R1 omega 2 R2 R3 R4 C4 2. The phasor diagram of Hayes bridge is shown below. Phasor diagram. The magnitude and the phase of E3 and E4 are equal and hence they are overlapping each other and drawn on the horizontal axis. The current I1 flows through the purely resistive arm BD. The current I1 and the potential E3 is equal to I3 R3 are in the same phase and represented on the horizontal axis. The current passes through the arm AB produces a potential drop I1 R1 which is also in the same phase of I1. The total voltage drop across the arm AB is determined by adding the voltage I1 R1 and omega I1 L1. The voltage drops across the arm AB and AD are equal. The voltage drop E1 and E2 are equal in magnitude and phase and hence overlap each other. The current I2 and E2 are in the same phase as shown in the figure above. The current I2 flows through the arm CD and produces the I2 R4 voltage drops across the resistance and I2 omega C4 voltage drops across the capacitor C4. Some advantages of Hayes bridge are: it can measure self-inductance with high accuracy for high Q factor coils. It has low power dissipation due to low resistance in arms BC and DA. It has good frequency stability due to negligible effect of stray capacitance. Some disadvantages of Hayes bridge are: it requires a standard capacitor of high precision. It requires a variable resistor R4 which may introduce errors due to contact resistance. It is not suitable for measuring low Q factor coils as it becomes insensitive to small changes in balance condition. Searching. Anderson's bridge is a type of bridge circuit that is used to measure the self-inductance of a coil. It was invented by Alexander Anderson in 1891. It works by comparing the unknown inductance with a standard fixed capacitor and using resistors to balance the bridge. The advantage of this bridge is that it can give accurate measurements of inductance without using a variable capacitor, which is more expensive and less precise. The disadvantage is that the circuit and the equations are more complex than other bridges, such as Maxwell's bridge. You can find more information about the construction, theory, phasor diagram, and balance conditions of Anderson's bridge from the web search results below. Owen's bridge is a type of AC bridge that is used to measure the inductance of a coil in terms of capacitance. It works on the principle of comparison, that is, the unknown inductance is compared with a known capacitor. The bridge circuit consists of 4 arms, one of which has the unknown inductance and resistance, another has a fixed resistor, the third has a fixed capacitor, and the fourth has a variable resistor and capacitor. The bridge is balanced by adjusting the variable components until no current flows through the detector. The balanced condition gives the relation between the unknown inductance and the known capacitance. Owen's bridge can measure a wide range of inductors with different quality factors.